Hello friends, continuing with the chapter of current electricity and the topic measurement of EMF. Today we take up part 2 of it, that is grouping of cells. Need. There are electrical circuits which need high PD for low current, and some circuits need low PD for high current. And there are third category of circuits which need high PD for high current for its operation. I repeat, there are electrical circuits which need high PD for low current, and some circuits need low PD for high current, and some circuits need high PD for high current for its operation. Such requirements of the circuit operation are fulfilled by grouping of cells, either by series grouping or by parallel grouping or by mixed grouping of cells. Mixed grouping means series and parallel combination both as per requirements. So thus there are three different ways in which we can connect cells. We can connect cells in series, we can connect cells in parallel, and we can connect cells in series and parallel combination, that is mixed combination, with respect to requirements of the circuit. First, series grouping of cells. A. Need of series grouping. When an electrical circuit needs high PD and low current for its operation, then cells are connected in series. I repeat, when an electrical circuit needs high PD and low current for its operation, then cells are connected in series. Now, how cells are connected in series? Let us see. When negative terminal of each cell is connected to positive terminal of the other cell alternately, the cells are said to be connected in series. I repeat, when negative terminal of each cell is connected to positive terminal of the other cell alternately, then the cells are said to be connected in series. Now look at the diagram. Here n cells are connected in series, where negative terminal of first cell is connected to positive terminal of the other cell, and negative terminal of the next cell is connected to positive terminal of the other cell, and so on. So thus this diagram shows that these n cells are connected in series. C. Equivalent EMF and internal resistance of the series combination of two cells. So let us first look at the series combination of two cells, then we generalize it for n cells. Now consider two cells with EMFs E1 and E2 having internal resistance R1 and R2 respectively, connected in series as shown. Let I be the current drawn from the combination, then potential difference VA minus VB is equal to E1 minus IR1, or it is equal to VAB. So let us mark it as equation 1. Now potential difference VB minus VC is equal to E2 minus IR2, and let it be equal to VBC, and let us mark it as equation 2. Now adding equations 1 and 2, Now we see that VB and VB cancels. We are left with VA minus VC. Okay. Now adding equations 1 and 2, we get VA minus VC is equal to E1 plus E2 minus I into R1 plus R2. Or we write simply VAC. This is the potential difference between A and C. That is equal to E1 plus E2 minus I into R1 plus R2. Or VAC is equal to EQ minus I R EQ, where EQ is equal to E1 plus E2 and is equal to sum of EMFs, and REQ is equal to R1 plus R2 and is the sum of internal resistance of each cell. EQ for equivalent. EEQ means E equivalent, equivalent of the combination. REQ means equivalent resistance of the combination. Okay. Thus, when we connect two cells of EMF E1 and E2 with their internal resistances R1, R2 respectively, their equivalent EMF adds up, that is equal to E1 plus E2. Similarly, internal resistance also adds up and becomes equal to R1 plus R2. D. Generalization for n cells in series. If n cells, each of EMF E1, E2, E3 and En, and internal resistance R1, R2, R3, Rn respectively are connected in series as shown, then E equivalent is equal to E1 plus E2 plus E3 plus so on plus En, and R equivalent is equal to R1 plus R2 plus R3 plus so on plus Rn. Okay, the equivalent resistance adds up, and similarly equivalent EMF also adds up when n cells are connected in series. E. Equivalent circuit. Now equivalent circuit can be drawn as shown in diagram. Now here this is the cell which has EMF as E equivalent, which is the EMF of the combination, and internal resistance REQ, which is the internal resistance of the combination. So we have replaced the n cells by single cell, which is equivalent to the combination of n cells in series. Now let I be the current that flows through the load. Then using Ohm's law, we have load current, that is current through load resistance R, say I, it is equal to EQ by R plus REQ, where EQ is equivalent EMF of the combination of n cells in series, and REQ is the internal resistance of the combination of n cells in series. Now discussion. Number 1. When EMF and internal resistance of each cell is same, that is E1 equal to E2 equal to E3 equal to En equal to E, and internal resistance R1 equal to R2 equal to R3 equal to Rn equal to R, then equivalent EMF EQ will be equal to N into E, and equivalent internal resistance REQ is equal to N into R. Then load current I will be equal to NE divided by R plus NR. Okay. 2. When external load resistance capital R is equal to NR, then power dissipation is maximum, because we know from power transfer theorem, when source impedance is equal to load impedance, then the power transfer is maximum. So because external load resistance R here is equal to internal resistance of the combination NR, that is the source resistance. So external load resistance is equal to source resistance, therefore power dissipation is maximum. And then load current is I equal to E divided by 2R, or it is equal to NE by 2R. So when we replace R, capital R equal to NR, then we have I is equal to E by 2R, and when we replace NR by capital R, then power dissipation will become equal to NE by 2R. Third point, when external load resistance R is very large as compared to internal resistance of the combination, then NR can be neglected and load current is I equal to NE by R, that is external load resistance. I repeat, when capital R, that is load resistance, is very large as compared to internal resistance of the combination, then NR can be neglected and load current is I is equal to NE divided by external load resistance R. And similarly, we come to the reverse case of it, that is capital R is very small as compared to internal resistance of the combination of the cells, then external load resistance R can be neglected and load current I will become equal to NE by NR, where N cancels, NN cancels, and we are left with E by R. That is, I is equal to E by small r, where small r is the internal resistance of each cell and E is the EMF of each cell. Okay. Now assignment 3.7 continued. Question number 5. The following graph show the variation of potential difference V across a combination of 3 cells in series connected to an external resistance versus current I. Now first, calculate the EMF of each cell. Second, for what current I will the power dissipation of the circuit be maximum? Assignment 3.7 continued. Question number 6. 3 identical cells, each of EMF 2 volt and internal resistance 0.2 ohm, are connected in series and further connected across an external resistance of 7.4 ohm. Calculate current flowing in the circuit. And here is the answer for it. Question number 7. 3 cells of EMF 2.0 volt, 1.8 volt and 1.5 volt are connected in series. Their internal resistances are 0.5 ohm, 0.7 ohm and 1 ohm respectively. If the battery is connected to an external resistance of 4 ohm via a very low resistance ammeter, then what would be the reading in the ammeter? And here is the answer for verification. Okay. So thank you. This is all about part 2 of measurement of EMF and PD of a cell. Next time we will go to parallel combination of cells. Till then, goodbye.